Okay. And good afternoon. We'll just give everyone time to get into the room today as we before we launch our webinar. But welcome to all those who are joining us. All right, I'm going to open this webinar, and thank you all for joining us today. My name is Tracy Ryan, and I'm with Ontario Soil and Crop Improvement Association, and I really appreciate everyone joining today. As we get started, I'll just let you know it is a webinar, and we're expecting approximately 100 people. And so we're looking forward to everyone's spending time with us. Thank you again for joining this Optimizing Nitrogen Efficiency for Best Practices for Sustainable Corn Production with Dr. Craig Drury and Dr. David Pelster. Before we get started, we'll just go through a few housekeeping items. So you know, your cameras and microphones are off. This is a webinar. And so if you have any questions, please put them in the question and answer, and we will be able to ask those for Craig and David after they've done their presentation. And any that we don't get answered, we will share their responses after the webinar when we make the recording available. So again, this is being recorded, just to let you know. I want you to check out our upcoming events under Living Lab Ontario. We have one on July 11th and one on July 18th, and you can find those on the Ontario Soil and Crop and Improvement website, and we'll put that up after. And again, just to remind you that if you've joined today and you have an on-farm climate action fund project in the nitrogen management category and are requiring a knowledge sharing event, this is a registered event. At the end of the presentation, you can scan the QR code on the screen and fill out the link that gets posted. There'll be an online form, or in the chat, we will post the link directly to the online form. So welcome. And just before we get started, I will just go over a few items about Living Lab Ontario. We are really pleased. This is our first public webinar, and it is great to be able to have so many people joining us. Living Lab Ontario is a project that is an innovative climate solutions, looking at co-developed practices that are tested on real Ontario farms. Living Lab Ontario is one of 14 living labs that are across Canada. It is part of the Agricultural Climate Solutions Living Labs project, and it brings farmers, researchers, and others collaborating on innovations to improve carbon sequestration and reduce greenhouse gas emissions, and provides other environmental co-benefits. So across Canada, we have many researchers, many farmers, many organizations, all working collaboratively within their projects on a variety of different initiatives that are of importance at a local level. The principles of a living lab are that they are user-centered innovation. So in an agricultural living lab, that means that the activities focus on the farmer's needs, and the farmers are involved throughout the process looking at the innovation. So the research project, the testing, the evaluating, and actually tweaking and improving the best management practices. It's all done collaboratively and through co-development. They work in partnership, so we have a variety of different disciplines working collectively and collaboratively as we move through with different, they come from economics, agronomic, socio. We've economics, we have those who work in biodiversity, so a wide number of different, and soil health, a wide number of different disciplines joining together to tackle the common issues. The other point being, and you're going to learn as David and Craig start presenting, that these take place on real farms at a real scale, so that we can have the feelings, the environment, the observations made by producers and how they fit within their operations, within their climate, within the different stresses that impact each and every one of their operations. Again, as I said, it's a look at this multidisciplinary approach, because it is really important that, you know, the adoption of an innovation is more likely to happen when it can be feasible, viable, and desirable. So it's got to meet all of those things. And through co-development, we can test and evaluate each of these BMPs under these different scenarios and approaches. And really, it is an innovation project supported by research rather than coming at it as a research project solely. We have over 40 farmers involved in Living Lab Ontario, more than 15 different researchers involved in testing, as you're going to hear today, nitrogen efficiency and use to increase profitability and reduce greenhouse gas emissions. We're looking at projects to increase soil organic carbon in cropland and pastures, cover crop grazing to improve profitability and carbon sequestration. We have producers who are looking at reducing methane emissions from liquid manure storages, and others who are looking at increasing pollinator habitat to sequester carbon and reduce emissions from low profit areas and other areas on their farm, as well as a variety of other projects that are integrated in. So in the future, you'll be hearing on these projects as well. But without further ado, we'll just acknowledge all of the funding partners and all the different collaborators involved in our project. And funding from the project has been provided by Agriculture and Agri-Food Canada under the Agricultural Climate Solutions Living Lab program, and by the following partners: Beef Farmers of Ontario, Dairy Farmers of Ontario, Grain Farmers, Ontario Federation of Agriculture, Ontario Pork, and Ontario Sheep Farmers, as well as having the support of a variety of different collaborators who are involved. And I am going to turn it over to Craig and hopefully give him slide control here. And Craig, over to you.
Okay, so I believe you should start by seeing a poll. We have 3 questions. If you could just take a minute to answer those questions. Just gives us a bit of a background information on where you currently are with your farming practice. You see the first question is, do you use inhibitors? So and if so, is it just urease inhibitors, nitrification inhibitors, or both? How do you apply your nitrogen is the second question. So if you could just take a minute and answer those 3 questions, and then we'll get started. As soon as the poll disappears, I'll
Yeah, we're still seeing it going up, Craig, so we'll end it in a few minutes.
just gives us a bit of an idea on where everybody's at in order to try and anticipate the interest and needs as well going forward with this program. Okay.
All right. Do you want to?
So 12% for urease inhibitors and 31 for nitrification, 31 and for both. And it's a real mix. Most surface broadcast incorporated, still the third surface, 31% streamed. What else do we see? 21% injected, 3% other. Cool. Okay. So quite a range of different approaches, which we want to always factor into. And then last, do you adjust your nitrogen rate are, and 62% are yes, and 17 no, and sometimes 21%. Excellent. That does help. So without further ado, I'm going to be giving you a bit of background. Our field study started about a month or so ago, so obviously it's a little bit too early to present any results from it. Hopefully there'll be other opportunities at workshops or webinars to discuss the work from the field trials. We will briefly give you a summary of what field trials are ongoing from a nitrogen standpoint near the end of the presentation. And if I have control, let's see now. Yeah, I don't yet.
Do you have, it says you have control. Sorry,
okay.
Craig. Let me.
Well, it's just not letting me do the pointer, but we can, or change sides. There we go.
No.
There it's Alice, but won't give me the pointer. But that's fine. So just as the topic here is optimizing nitrogen efficiency. So we're looking at best practices for sustainable corn production. So I'll be starting off this presentation. David will talk about sort of the tower ways of measuring N2O and some of his data. And Pam has provided an update on this year's field trials that are ongoing. So overall, I mean, the objective of the research that we're conducting, and hopefully the on-farm trials that we've initiated this year, are really to develop nitrogen management strategies, which really have two objectives. Of course, we want to enhance yields by reducing the losses of fertilizer through nitrous oxide emissions, ammonium volatilization, nitrate leaching. And we also have a target, try to reduce nitrous oxide emissions from fertilizers by 30% by 2030. So we're trying to achieve multiple objectives with these studies. Seems to be a bit of a lag changing slides here. There we go. So really, we all nitrogen researchers have our own version of this slide. This happens to be the one that I came up with. And they all have the same elements. And what I want to focus in on is really the fact that we have a lot of red circle areas on the slide, and those represent losses of nitrogen fertilizer. So it could be lost through ammonium volatilization, which is in the center of the screen, or denitrification occur, which is more, wish I had the pointer here, middle of this screen, or nitrate leaching below the soil profile, which is the bottom right of the screen. We can also have surface losses through tile drainage, again, in the left part of the screen. So the catch is we see that nitrogen transfers through through fertilizer and through the soil. And what we want to do is really try to enhance the amount of nitrogen that goes into the crops and minimize the amount that's lost to the environment. And there are many losses, so it becomes a real challenge to do that. Another way we've come up with to try to describe this whole process in a more stylized or conceptual model approach is looking at the whole fertilizer transformation as a pipe and valves. So this is just the pipe part of it. So at the left, you can see we're adding fertilizer. In this example was urea. And shortly after application, the urea hydrolyzes in the soil, and we can lose ammonium up to the air. And so once it's lost, it's no longer going to be available to the plants. A little bit after several weeks, then the ammonium, NH4+, that stays in the soil is nitrified. And during that process, if we have a heavy rain event and the soil becomes saturated, another process can occur called denitrification. And that one allows for the losses of nitric oxide, the NO, N2O, which is the greenhouse gas we want to reduce. And also the third pipe on there is N2, which again is part of the air that we breathe. And it may not be an environmental contaminant, but clearly it's a loss of expensive fertilizer. So the plant at the end really gets the nitrogen that's left over after all the losses occur. And again, if there's a lot of rain on the bottom of the slide, you can see that there's nitrate coming out through the profile, may come out of tiles as well. And so really the plant is only able to use the nitrogen after all these losses occur. So we're going to take that same diagram and we're going to add valves to it. So in the first case, that top graph in the middle is really what I was first describing. So that's sort of the business as usual without any 4R practices. And here we're talking about 4R practices as being like a valve. And so this case, our valve in the pipe is our 4R practices where we use a nitrification inhibitor. So that nitrification inhibitor in that diagram keeps more of the nitrogen in the ammonium form longer, which unfortunately can increase a little bit of ammonium loss on that first pipe. But all the other losses, the NO, N2O, and N2, are a little bit lower than we saw in the business as usual model. And so we still have the plant using the nitrogen that's left over. Because we've decreased N2O and N2, but increased ammonium, we may not have changed the amount available to the plants just using a nitrification inhibitor. However, if we add a urease inhibitor, because we have found that ammonium volatilization could be responsible for up to 50% loss. More typically, it's 20-25% loss. But when we decrease such a large loss mechanism in the process, in fact, there might be more nitrogen available to crops. So we have, 2 plants or, instead of 1 to illustrate that. But you can see we can increase the amount of N2O compared to the business as usual diagram. So what's the solution here? If we just sort of put one valve in, it can affect one process, the second valve, the second one. But if we maybe stack processes and look at a couple of combinations together, and okay, we get our 2 or more practices, we might be injecting UAN instead of urea, adding maybe a urease inhibitor, or as I mentioned, adding a nitrification inhibitor. In this particular scenario, you can see that multiple losses of N have been reduced compared to our starting point, or either of our once nutrient practice. And the end result is we have greater N going into our crop. So that's the theory. So what I'm going to do is I'm going to take you through 11 years of research. So I started in 2013 looking at both ammonium loss and with wind tunnels and N2O. And again, we're trying to use nutrient stewardship practices. We've varied sources of nitrogen, whether it's adding urease or nitrification inhibitors, timing, whether it's added all beginning of the season, or we move some of the nitrogen to a side dress. We're looking at optimal placement, so targeting the crop root zone. And ultimately, if we can really tweak and get the system more efficient, we should be able to reduce the nitrogen rates if we've managed to reduce some of the losses. The other factor that's to be considered is soil health. Again, these losses are minimized if we have a healthier soil with higher carbon levels. And we can achieve this sometimes with cover crops, crop rotation, conservation tillage, and other ways of trying to build up soil carbon levels in soil. So way back 2013-14, we started building and deploying these wind tunnels to measure ammonium loss. We take a gas sample, sort of the beginning of the wind tunnel, an air sample. We have another gas sample at the end of the tunnel, and we look at the differences in concentration of these gases, and we use that to estimate our losses. So in this particular year, back in 2014, we lost when we had broadcast urea. We were losing, that's the top graph, about 40 kilograms of N. That's with just urea. When we added Super U, which is the urea with the dual inhibitors, we dramatically reduced ammonium loss. So it dropped from 40 down to about 10. If we just injected UAN, this is the bottom graph in red. If we injected UAN, it drops also about 10. But injecting and stacking practices, by injecting with the two inhibitors, we eliminated losses. So in this particular case, here we're looking at N2O emissions. Remember before I said if you just add a urease inhibitor, we can see higher ammonium loss. And this actually shows it quite nicely. That yellow bar happens when we just add urease inhibitor. Our N2O emissions can go up. However, if we take the reference broadcast urea, that first red bar, and we look at a dual inhibitor, in this particular example, we have a decrease in N2O emissions about 12%. If we inject it, we also have a decrease in N2O emissions, but injecting with inhibitors, we also have a decrease. So in this particular example, inhibitors help, the dual inhibitor helps, but a urease inhibitor doesn't help as much. In fact, can increase emissions. So, and what happens with yield? Well, we see that if we look at the red bar with broadcast urea, if that's our term of reference, by adding a urease inhibitor or Super U, the dual inhibitor, we have 5% yield increase. Whereas just injecting alone, changing how we place the nitrogen, we had a 10% yield increase. And the combination of injecting and inhibitors, our yields increased by 18%. They went from about 172 bushels up to about 205 bushels. So that certainly is quite dramatic and would pay for the cost of the inhibitors. In another study, we can't look at all these different factors in one study. So I'm going to give you some examples of what happened when we looked at, in this case, the timing of nitrogen. So over a 3-year average, with pre-plant nitrogen, with adding a urease inhibitor, that's that first yellow bar, our N2O emissions go up because we're just targeting urease and not N2O. But when we add the dual inhibitor for pre-plant or side dress, that green bar, we see up to a 34% reduction in emissions, which in fact is close to the target we want to reach. So by going from pre-plant to side dress, there's a benefit because we've avoided losses that can occur over that first 3 or 4 weeks, and we're putting the nitrogen at the time closer to when the plants can use. And it works especially with going side dress or side dress to inhibitors, but not so much with just urease inhibitor on its own. And again, we see if we go compare our yields with pre-plant to side dress, we see a 14% increase yields. We've avoided some loss by delaying application, and there's been a benefit. So moving on, if you add all your nitrogen at front, right at planting, we thought, okay, but we do have another option if we do that. So, you know, we could add urea's broadcast, which is the first red bar, or the second bar on your screen is broadcast with the dual inhibitors. And there we see a 50% decrease. Now we're talking about ammonium volatilization. So instead of losing 22 kilograms, we've dropped it to 10. So that 10 is there and now available to your crop. Broadcasting incorporating helps. So just by trying to work it into the top inch or two can decrease ammonium losses, you know, again, from about 22 down to about 14. But again, with broadcast incorporating that second green bar, with the inhibitors, even greater reduction, probably around 60%. However, if you look at the last two, if we inject nitrogen in soil, especially if we use packing wheels and such, we can actually almost eliminate losses. And if we look at our yields, going from broadcast, the first red bar, to broadcast injection, second red bar, we have a 3% bushel increase, 4% with the third red bar with injection. But when we go and start adding inhibitors, we see about a 9 to a 13 bushel increase over this 3-year period, I'm sorry. We then sort of said, okay, we know that injection works, but is there different ways to inject to improve it even further? So in this sort of third study that we conducted, we compared broadcast urea on the left to either a single slot injection, so just putting it sort of between one slot between the two rows of corn, or in the bottom right, the double slot. Here we're adding the same amount of nitrogen, but we're putting them into two different slots. And why do we do this? Well, the way the losses go, they're a function of how the chemistry is associated with the urea hydrolysis in particular. When urea hydrolyzes, the pH of the soil goes up. The higher the pH, the more losses occurs. So if we add the nitrogen in a double slot, we're adding half amount of nitrogen in each slot. With half amount of nitrogen in each slot, pH won't go up as high, and the losses should theoretically be lower. We compared this, and in fact, this is what we have found, and I'll show you that in a minute or two. The other thing from N2O perspective, it's a rate factor. So the more nitrate that's present in the soil in any one zone, the higher the N2O losses. So by splitting the application into two rows, the concentration in each band is lower, and we can also hope to have lower losses. So let's go to the next slide. So I'm not going to go over this too much, just to show you how we measure it. We measure it every day. These are losses every day. Sometimes the losses, if the soil is so dry that the fertilizer isn't even dissolving, the losses can be very low. In fact, if you look at that red bar in the bottom, some of the peaks where ammonium is converted, or urea is converted to ammonium, can occur even 10 to 12 days after application. It's not instantaneous. And then if we look at adding those daily values every day, in this particular year, we lost 10 kilograms with broadcast urea. With the Super U, the broadcast, the dark blue on the top, we decreased that quite dramatically, over 50%. Single slot injection had the highest loss, and you can see in the slide in the top. And that occurs when you don't have packing wheels, or they're not effective at closing the slot. You can still have some airborne loss. But here, if you look at the double injection, the bottom graph, where you don't have as much N in each slot, but still the same N application rate over the whole field, much lower losses. And with the double injection and the green, the dual inhibitors, we've eliminated loss. Okay, so if you look at cumulative losses, the average over these 2 years was about 13 kilograms of N. In that first broadcast urea, dramatic reduction in loss when we added Super U with the dual inhibitors. Just by going to single slot without inhibitors, we're able to decrease loss by 23%, which is that first red bar, or by 65%, which is the second bar. And then the combination of double slot and the inhibitors, or single slot the inhibitors, had dramatically lower losses. So that's for our ammonium loss. And let's look at the next one. And again, yes, as I said before, losses can be decreased by 84 to 97% with injection and the two inhibitors. We also measured nitrous oxide emissions. We take many samples, typically 35 times over the growing season. They occur primarily after N is fertilized in our soils in southwestern Ontario. And they occur, if you look at the top, these are after rain events. The higher the rain, especially earlier in the season, the wetter the soils, and the higher the losses occur. And that affects the cumulative losses. And I'll just go through the summary here. So if we look at our highest loss, we're losing 7 kilograms of what was applied with single slot UAN injection. With the green, which is the middle green bar, we're decreasing losses by 16%, or the double slot also, the third red bar decreased by 16%, but double slot injection, dramatic decrease in losses by 53%. Now we see that broadcast urea has lower N2O emissions. Part of that is because there's so much ammonium loss that there's not as much N left in the soil to be denitrified. So we really have to look at both in terms of a balance sheet approach. And we see here with the double slot injection, our yields increased by about 7 to 13%, better than the single slot, better than the broadcast urea. And we've also looked at late season application when you add, the nitrogen, maybe when the corn is sort of 10 to 12 leaf stage. In those cases, we've measured ammonium with urea application of 55 to 58% over the last 2 years, whereas we're able to decrease it anywhere to 15 to 21% by looking at UAN application. Again, it's just on the surface because you can't inject easily when you have 3 feet, 4 feet tall corn. But by putting it as UAN and adding a urease inhibitor, we were able to decrease losses. But it still, the nitrogen wasn't as effective as side dress application. And this is sort of the last sort of example I'm giving of, okay, let's sort of go beyond the 4R practices and saying, if we start looking at them with cover crops and inhibitors, what can we find? Here with ammonium volatilization starting out, the average over 3 years in this particular study was very high. We applied about 160 kilograms and lost over a third of that, or about a third of that to ammonium volatilization with broadcast urea. The first green bar, 43% reduction in loss, injecting anywhere between 95 to 100% injection. So the first 4 bars are with no cover crop. The last 4 bars are in where we had killed out a rye cover crop in the spring. We could see that just by growing with cover crop or applying cover crop, we had a 90% decrease in ammonium loss, which is sort of the third red bar. 63% was broadcasting urea with the dual inhibitors, the green one, under a cover crop, and injecting, we actually had eliminated the loss. We can actually see ammonium deposition going on. And in terms of N2O emissions, we also saw this benefit of decreasing N2O emissions by 33% comparing to injected UAN with the dual inhibitor. And then if we look at the last 2 bars, injecting with a cover crop is 27% lower N2O emissions, or 35% when we injected with cover crop and the 2 inhibitors. So combining cover crops and inhibitors has worked both for ammonium and N2O emissions. So if we looked at the combined effect of both of these, we start out with over 50 kilograms lost, and we can see if we go through all these different scenarios, if we inject and have cover crop, the combined ammonium N2O losses is 90% lower. Corn grain yields had increased quite dramatically. Over the first couple of years, we saw up to a 25% increase in yields when we inject, and we inject that last green bar with the inhibitors. And the reason why I've split this graph is to sort of focus in on, okay, the first set of bars have no cover crop. The next set of bars have cover crop. So cover crop along with broadcasting urea, we had a yield penalty. So what is happening here is that as the cover crop decomposes, we're putting the nitrogen right on the surface. That nitrogen is being used by the microbes to decrease or to decompose the cover crop. However, the good news here is if instead we have a cover crop, but we inject it, typically 3 inches down, 70 centimeters, we're below that active decomposition layer, and we still see the benefit of injecting even in the cover crop system. So we're able to overcome that yield penalty. And I'll let David take over from here. Thank you.
All right. Hopefully I can take control here and advance the slides. If I don't yet, that'll come soon, hopefully. Yeah, there we go. I can advance the slides. So I haven't done nearly as much for our research as Craig, but I do have a data set that sort of measures the losses in a very different way. Through the slides that Craig had, you would have seen a bunch of these little chambers, and you're using those to measure the emissions, but it's pretty small area that's being measured. And the one thing we do know about N2O is that there's a lot of spatial variability. So what we've done is we have what's called micrometeorology tower, and I'll show you a picture, but this is the field that we have. We actually have data from 22 years. I'll just be talking about the last 7 years when we've been comparing dual inhibitors to just regular urea. So the field here, it's just south of Ottawa near Barrhaven. It's with the CFIA, so the Canadian Food Inspection Agency. They have a farm there. It's 27 hectares. It's split into 3 different sections. It's silt, clay, loam. Yeah, so the 3 sections that we have, let's see how long it tried to move it forward. There we go. Okay, so you can see it's split into 3 different sections. So the conventional treatment is on the edges, and then you have the dual inhibitors that used in the field in the center. So we have two towers set up, and they will be measuring, and they have it's pretty complicated system. I still don't fully understand it, but essentially it's using the flux gradient method. So you have 2 different heights where you're measuring the concentration. You have a sonic anemometer that measures wind speed in 3 dimensions, and using your vertical wind speed and the difference in the concentration in intake 1 from intake 2, so the 2 different heights. So with vertical wind speed and those differences in concentration, you can estimate your flux from your footprint area. Your footprint area changes a little bit with wind speed. So slower wind speed is generally a bigger footprint area. But you can see there, the footprints are sort of highlighted in sort of a lighter green. That would be sort of with the prevailing winds. And so with the prevailing wind kind of from the west southwest, most of your footprint is going to be like for the west tower, your footprint is going to be in the regular treatments, and then on your east tower, so the tower on the right, that'll be coming from your sort of improved, so the dual inhibitor treatment. And then in the center, we have, it's a laser analyzer. So it's analyzing in real time and continuously. There are sometimes where the data isn't really viable. And that's usually, sometimes if you get an ice storm, it can cover up the sonic anemometer, and then you don't get good wind speeds. There's a few other times where it doesn't work, but in general, you get, 12 months of data, or maybe maybe 11 months of data, and almost 24/7. So it's sort of semi-continuous measurements. We also do a bunch of other measurements at the site too. We have weather stations, so air temperature, humidity, wind speed. We have incoming radiation, heat flux, and then we have soil temperature and moisture sensors. We collect a lot of crop data, and we also measure different soil properties through the year. So this is sort of what the data looks like over the last 7 years. So you have the red, which is your inhibitor, and your blue, which is your the conventional treatment. And you can see throughout there is a little bit of a gap. We tend to take the equipment down around Christmas in for servicing. We've been trying to shorten the gap that it's out. So if you look at 2023, there's a pretty short gap there for when we needed to take it into the field. The sort of shaded blue, that's your snowpack. But you can see we can measure the emissions pretty much through the entire year. And what's shown here are your weekly fluxes, but this is a cumulative of half-hour fluxes that we measure throughout the entire period. So the one thing we've noticed with this sort of measurement is you do see a bit of a peak happening before you apply the fertilizer, and that's pretty normal. You have sort of a buildup of your residual N that is left in the field after harvest, and then you sort of have a buildup of available nitrates, and then as the snowpack melts, you have a lot of water that goes in. The soil starts to warm, and so you have this pulse of this pulse of nitrous oxide emissions that come out in the spring. We also have, this is sort of the peak that happens just after you apply the fertilizer. So as Craig says, you apply the fertilizer, and shortly afterwards, if you don't have any inhibitors or anything controlling the amount of nitrate, you can see a pretty big peak in nitrous oxide emissions. And then you sometimes get sort of an additional peak, and that's usually related to some sort of really high rainfall events that happens while there's still generally before the crop gets really big. And then occasionally you see a little bit of a peak again after harvest. So after the crop senescent is removed, you have the decomposition of the roots, and that can lead to a little bit of a pulse happening in the fall as well. So what do we see for reductions? We have this, like I said, this is the last 7 years. So we've had 4 years with corn, 2 years with wheat, and 1 year with soybean. Obviously, with the soybean, we didn't use inhibitors. We didn't really use fertilizer at all, just a small starter. Just the, what is it, ammonium phosphate, more for the phosphate than the N. But what we've seen is that, when you look at it, you have the conventional on the left of the screen and then the dual inhibitors on the right. And we've broken this down into different periods after the fertilizer. So the dark blue at the bottom, that's your 30 days post-fertilization. The sort of orange is your growing season. So after that 30-day period, the rest of the growing season. And then the gray is sort of just after harvest. The yellow is your fall and winter, and the blue, the sort of light blue at the top, is the spring melt. And if you look over at the dual inhibitors, you can see the reductions. And if you look at the top, that's sort of your reductions over the entire year. So if you look in the top light blue, 2017, it's -5. So it actually, the dual inhibitors had emitted 5% more. So not very good year, but we had some very strange, really, really heavy rains just around fertilization. So not exactly sure what happened, but that seemed to affect the efficacy of using the inhibitors, having these really heavy rains. The other years, 15% reduction in emissions in 2018 and 2021, which was the next corn year, is 27%. And then last year was 8% over the entire year. But the one thing that's interesting, and it was nice to see a lot of the people in the poll had mentioned that they adjust their N rate based on the 4R treatments that they use. If you look at the reduction over the, the 30-day post-fertilizer application and over the entire growing season, you see a 24% reduction in 2018, 48% reduction in 2021, and then a 29% reduction in 2023. Just over that growing season. And in this trial, we applied the same amount of fertilizer. So what it looks like, we didn't see any increase in yields. And so what it looks like is that at the end of the growing season, we had sort of a surplus of N in the soil that was left. And that led to higher emissions from the field that was treated with the dual inhibitors through the post-harvest period, the winter, and then the spring snowmelt. So some of the reductions that you saw over the growing season, your reduction over the entire year was left, and we think it's because because we're not seeing a yield increase, we should probably be applying less nitrogen with the dual inhibitors, just because otherwise you're leaving too much nitrogen in the ground at the end of the growing season. Okay, there we go. So the other thing that we noticed is that the wheat years, so when we grew wheat, we didn't see any change in yields, and we didn't see any observable reductions in N2O. In the corn years, we did see a bit of a decrease there. So, and like I said, with the 1 year where we actually had a slight increase with the inhibitors, we think that relates to the really wet spring that we had. Maybe it'll be the same thing this year too, because it's been a wet spring, I think, as well for us. Yeah, it's a good question. I just saw the one pop up in the chat. I mean, I don't think we need to reduce it very much, but we've been talking about maybe a 10 to 15% reduction. But yeah, the annual reduction, what we've seen is that in the corn years, you generally see a reduction. Nothing happens in the wheat, and then the soybean, the difference between the two plots, may not even be related to the inhibitors anymore. That could just be, I'm not sure what's driving that, but yeah. And that's okay. There we go. Yeah. So these are all, what we've done on the experimental farms. This year we have a number of different sites on producer farms where we're looking at, we have inhibitor trials. We have, looks like 5. I've got 3 trials where we're doing N2O measurements. Craig has 2 down in Southern Ontario. So we have one around Peterborough, one south of Ottawa, and one west of Ottawa, and then the 2 in sort of southwestern Ontario there that Craig's leading. Then we have a number of strip trials that we're doing that AAFC is leading, or OSCIA is leading, where we're looking primarily at the effect on the yields. Craig, I don't know if you have anything more to add here. If you do, just jump in.
No, I'm good.
Yeah, so like I said, we've got a number of different farms where we're measuring emissions and looking at yield effects and everything. So Harrow, Tilbury, and these are the different treatments. And as you could see, there's the one question I had, what sort of reduction would you suggest? So you could see a lot of these are 85, 90% of what the recommended rate is. And that's sort of what we think should be effective. So you should, and in all these, because we haven't seen, although Craig did see a bit of an increase in crop yields, I haven't. So, if you're not seeing, and that's something, as farmers, you can try it the first year at 100%. If you don't see an increase in yields, then drop your rate a little bit and see what happens. So for all these farms, it's about 85%, 90% of what the typical rate would be. And there we go. So with the living labs, we have there's a number of activities, field selection, the trial design. We've been working with the farmers to see what they're comfortable with, what they're interested in doing. Each of the farms where we're doing the N2O measurements, we have weather stations out there. We've done baseline fertility sampling. We're looking at soil mineral nitrogen throughout the growing season. We're doing nitrous oxide emission measurements. We're doing those weekly, and then we'll look at planting grain yield at the end of the year, and then biomass as well, biomass carbon and nitrogen through the year, so we can get an idea of how these different treatments, not only what it means for emissions, but what it means for the crop as well. And Craig, I'll let you talk about this again.
Oh, it's just sort of the summary that nutrient management can achieve a lot of benefits. The 4R, better placement, timing, source, rate. Conservation ag can also be beneficial, whether it's a better crop rotation or diverse crop rotation, cover crops, reduced tillage, conservation tillage. So it's that combination that we can achieve even greater yields and lower nitrogen losses. And you have to, I think you still have the control of. Yeah, just the take-home messages. Basically, we found benefit with side dress nitrogen application. We found benefit with the dual inhibitors in decreasing both ammonium and N2O emissions. Improved placement, the dual injection system seemed to really work for multiple benefits of ammonium losses, yields, and as I mentioned just a minute ago, conservation ag practices. If you want to just take the acknowledgement, of course, a lot of this research has been possible because of funding from various groups, including Green Farmers, Fertilizer Canada, OSCIA. We've had Foundation Food and Agriculture Research help funding some of this research in Ag Canada. And then we'll end it here and with the next slide and open it up for questions.
Great. Thank you both. And I will just take back slide control here. And hopefully we can make sure that we have the off calf. So questions. I know that we had one that David's already answered. How much do you suggest reducing your nitrogen rate if you use dual inhibitors? Are there any other questions? There we go. There is one from Brian there in the Q&A. If you use a Y drop later in the season, will UAN inhibitor delay the plant uptake, conversion of NH3? If we have enough rain immediately following application, it will enter the soil profile and less loss risk without using an inhibitor. I'm not sure who wants to tackle that.
Okay, I could start, and then David, if you wanted to chime in afterwards. So let me just tell you one story. Back in 2014, it was the day 10, and it was a Saturday, and I was going out to change the traps on those wind tunnels. Overnight, we had 3 inches of rain. I went in the field, and we had good surface drainage, but at that point, the field was a lake. With all the wind tunnels there, they're all powered by electricity. Fortunately, we had the lines above the water level. And I thought, okay, well, we're done with all this rain, 3 inches of rain, saturated surface. We won't have any more emissions, right? So I unplugged everything, went back on the Sunday, and indeed, there was no surface water. It was saturated in the surface, but no ponded water. I plugged those tunnels back in, and sure enough, 2 or 3 days later, I start to see the ammonium peak returning. So yes, rain will help reduce losses. So it will help dissolve some urea and move it in the soil, but it doesn't move it that far where it eliminates it. So yes, a good rain after any surface application will help reduce losses. But if it's still within that top inch. There's a lot of pores there. When hydrolysis occurs, losses can still occur. So again, especially with surface application, really suggest including if the late season application, try to include a urease inhibitor.
Yeah, I'll just because he asked if the inhibitor delays the plant uptake, so it's using UAN in a Y drop. If it's gonna delay it, I think he's worried about it not being available for the plant to use. But UAN, you have both urea and ammonium, so the ammonium is going to be available right away, and the urease inhibitor is just going to delay a little bit the conversion of the urea to ammonium. So, I mean, I'm not, yeah, I'm not entirely sure if it's going to be an issue with the Y drop if you're using UAN because you have that ammonium that's available immediately anyways.
And if I may, there's one other thing to consider though with late application. So if you consider the roots aren't all at the surface, most of the roots are going to be, 6, 12 inches down in the soil. If it's really late in the season and all your nitrogen's at the surface, the only way that nitrogen is going to get to the roots is if any urea is hydrolyzed ammonium, ammonium nitrified to nitrate. Nitrate is negatively charged. It's not held by the soil, so it will move with the rain. But if we have an extended dry period after late season application, the roots may not have access to that nitrogen that sits on the surface. We really need that rain, if it's a late season application, to pull the nitrogen down to the roots. So that again, is another perhaps risk associated with late application in terms of root access of what you've applied.